Hello, everyone.
Hey, Mr. Minsky, I'm in Utah for a water polo tournament right now and I can't make it to class today. Can I
Oh,
just take the notes another time?
yeah, no problem. I'll post the notes and I should get the video posted as well.
Okay, perfect. Thank you.
Okay, good luck.
Thank you.
All right, everyone. Good afternoon. Um, okay, so let's get started. I want to go over a few things that you need to know to be able to answer the questions on the homework. And today's lesson will be, unfortunately, a little bit, part of it is going to be teaching math in a way I don't really like that much, where it's just kind of like, I give you this, I'm going to give you this formula, and I'll show you how to, like, the pattern and how to remember the formula, but we won't really get a chance to really explain the formula too well in this class. But it is a useful formula, and it's the formula that basically gets you out of having to solve a system by doing elimination. Like, you can just do this formula and you're going to get the answer. Now, it's a bit of work to do the formula to get each answer, because, like, if you have a 3 by 3 system, for example, you need to get 3 answers. So you need to use this formula that is called Cramer's rule. You're going to need to use this formula 3 times. So that's going to be the goal of today, is to get you to Cramer's rule. Uh, and and then on Monday, I'm going to show you another idea related to back to geometry, which will maybe give you a little bit of insight into why that rule is true, and some of the things in that. Um, but um, but first, I'm just going to show you kind of what the book shows you about, like, what the formula is and how to do it. And it's like a really, you can think of it today as a really neat, systematic way. Like, it's always the same pattern every time to get the answer of a system. And then on Monday, I'll give you a little more insight into some of these things. Okay, so let's just start off with a 2 by 2 system. Let's do the 2 by 2 in a very abstract way. So we've done a lot of these, right? We've solved things like this: ax plus by equals e, and cx plus dy is equal to f. And they go through this example in the book. So today we're going to learn about determinants. Determinants of a matrix, and Cramer's rule. And in this class, we won't really do a full explanation of Cramer's rule, but we will on Monday. Today, I'm just going to show you the formula for this determinant and tell you what it is, and show you the pattern. But I will show you what it means, what the picture of it means, and how to actually interpret it. It's really, really cool. We'll talk about that on Monday. Okay, so in this question, we want to solve this 2 by 2 system, like that. So we want to solve this for x and y. And we're setting this up with a, b, c, d as our coefficients, and e and f as the target. And we just want to come up with a way to do this, because we don't really care what the numbers there are themselves. We just want to know a general procedure regardless of what the numbers are. So anyone have a good idea how we can set this up? What we can do to this system of equations? you think of A, B, E, and C, D, F as like fixed numbers. So what's a good step we could take here to solve, let's say, for X first? Any volunteer want to explain kind of what you could do here to get one of the variables? You could do a matrix thing. You could write it like this, but let's kind of not do the matrix. Just, the matrix is just like a shorthand essentially for the system of equations. So let's just stick with the system of equations for now. But yeah, how could you cancel them out? What could we do to eliminate some of the variables? Or eliminate one of the variables. There's only two variables. Even though the other ones are letters, they're not really variables per se. We're thinking of them as constants. So that's a good suggestion. If we make one of them a negative, that might do some canceling for us. But would that be quite enough? How could we adjust each row to cancel out a variable? Anyone have a good idea? So far, yeah. So far, there's been some good ideas to maybe write it as a matrix. But I think, yeah, I think to just keep it as a system for now might make it easier to follow. So we encountered this with actual numbers. Usually we just make we multiply one of the rows by something to get it to cancel, to get it to match the other row. But we have encountered examples where there's in front of the X and Y, we could try to do substitution. That would be a little bit intense, but that would work. A substitution is a good strategy. It wouldn't be that intense, but that would be good. Does anyone see a nice way to do elimination? Well, let's say I wanted to eliminate X. What would I need to do to the equations, like the first equation and the second equation, if I want to get rid of X? And Kenji was very close. You said you wanted to cancel them out. But before you subtract, what do you need to make sure about the X? You want to make them the same. So what can we multiply the first equation by and the second equation by to make them the same? Nice, Lily, yes. So we can use the coefficients A and C, multiply the first equation by C and the second equation by A, so that they cancel. So let's do that. So let's say we want to eliminate X. So to eliminate X, and our goal will be to finally just get a formula for X and Y only that depends on A, B, C, D, E, F, only those numbers that were given. So to eliminate X, we write the following. To eliminate X, we multiply the first equation by we multiply the first equation by C and the second equation by A and subtract. And let's see what that gives us. So if we multiply the first one, we get ACX plus BCY equals EC. And I'm putting the C next to the A and B, not on the side of the X, because I want to think of these as, remember, X is like my variable, and that's the thing I'm actually solving for, and the other things are the coefficients. And then if I multiply that one by A, I get, let's say, CAX DAY. And in fact, I'm just going to write it. I'm going to rewrite it. I'm going to always write it in alphabetical. Why not? I'm going to write ACX ADY equals AF. Maybe the last one should be. So that's just multiplying everything by A. Now let's subtract. So when we subtract it, we get the following expression. So these will cancel. These are gone. And these both have a y in it. So when you subtract them, you just have to subtract the coefficients. So you get BC minus AD times y equals AF minus EC. Oh, sorry, the other way, of course. EC minus AF. And then dividing it, you get this nice kind of formula, which is, on the face of it, doesn't look too bad. You get EC minus AF all over BC minus AD. Okay. Any questions on the steps that I took to find y? If you notice, there's no more x here because we eliminated it and we were able to get the exact number of y in terms of the coefficients and the target numbers that were given in our system. Please hit the yes button if you are comfortable with the steps that we took there and you kind of see that, this formula, when you're doing elimination, essentially you're just redoing these steps over and over again. So if you just memorize this formula, you could actually save yourself some work. And also this formula is a little bit annoying to plug in because you have to, you have 6 numbers and you got to arrange them and do some computation with them. Awesome. Okay, so I want all of you to now please do the same thing, but eliminate the y and get another formula for x. Okay? So let's eliminate, this time let's eliminate y. And I'll give you a few minutes to tell me what final formula you got and solve for x. And by the way, I'm going to rewrite this. I'm going to put a minus sign on the top and bottom here to make it more consistent with the pattern that I'll show you in a little bit. So this will become AF minus EC. So I'm going to switch the subtraction in both of them. That doesn't change the actual answer. Okay, so yeah, I will ask you guys to please do the same steps. If you're a little bit stuck on what to do now, message me if you're not sure kind of what I'm asking for here. But do the same exact thing, but instead of getting a formula for y, please try to get a formula for x. Let's see here. And message me when you got the answer. I'll give you some feedback. All right, so far we got one student who got it. That's great. Nice. Let's see here. All right. Okay, let me ask, Gabby, do you want to share kind of your steps and I can write them and just walk us through it?
Oh, yeah, sure. So I started with like the equation from the top. I just wrote that down again to give me a better sense of what I was doing.
Good.
And then from there, I kind of saw that you times in the beginning, you times A by the first equation by C and the second equation by A. So what I did is I timed the first equation by D and the second equation by B, so that
Perfect.
the B, dy, like both of them cancel out.
Nice. And then this one by B, and then you subtract, right?
Yeah, and then when I subtracted, I got parentheses AD minus CB parentheses X equals DE minus BF.
Perfect.
And then I divided by AD minus BC from X, and I got X equals DE minus BF over AD minus CB.
Excellent. Awesome. Thank you, Gabby. That's great. AD minus BC. Okay. Let's see here. Olivia, did that help?
Yeah, it did. Thank you.
Cool. Yeah, so there's a lot of letters floating around, but what's ended up happening is you have these expressions that look a little bit complicated, but you're just kind of saying, okay, well, I got rid of one of the letters, and I can divide by this weird expression, 80 minus BC. Awesome. So that's our system. BF. Oh yes, Kanjit, if you wrote BF minus DE, your denominator should be BC minus AD. So it's okay, like if you have a fraction and there's a subtraction in the numerator and there's a subtraction in the denominator, it's okay if you switch the order of the subtraction as long as you do both the numerator and denominator are switched. Let's see. Okay, let me take a look here. And I was looking at ACX, BCX equals EC. So the goal was to eliminate in the first example is to eliminate the x variable. So I realized that, I think Lily suggested maybe multiplying this by C, the entire equation, and multiplying the bottom one by A, that would make them both have AC as a coefficient. So when you subtract, they would cancel. Oh, okay, good, cool. Is it okay now? Awesome. Okay, just going to address a few more questions here. Allison, how do you know which ones go on top and which ones go on bottom? Do you mean in the final answer, like which what's on the numerator, what's on the denominator?
Yeah, because I got the same like letters, but I mixed them up and I'm just confused.
Yeah, it's definitely possible to mix things up here. Were you okay with kind of what Gabby described, like right here?
Yeah, no, I got that, but when I got like, oh my gosh, what I got was X equals AD minus CB over ED minus BF. But I just don't know, it was like, is that okay, or do you need to make sure like one goes on top of the other?
No, yeah, you definitely want to make sure the reciprocal, definitely want the reverse, numerator and denominator
Okay.
So it's just from this equation though, because you just have to divide, you cancel out this term. So this thing will be on the denominator of the expression that's on the right side.
Okay, wait, I get it now. Thank you.
Mhm.
I am.
Let's see. Kaden, let's see. Why did you multiply by d and b? Wait, Kaden, very good question. So that's to eliminate, when we want to solve for x, we want to eliminate y. So here there's a by, and over here there's a dy. And unfortunately, I can't just subtract because that would be, they're not the same. So the trick is multiply the first equation by d, the entire thing. That will turn this into bd, and multiply the bottom by b. It's the same thing from the previous one. And then when you do that, these guys cancel, and you're just left with what you would get when you have AD and then BC. Okay, did that help a little bit? Awesome. Nice, Jack. Welcome back. Yeah, you could do exactly the same thing with matrices. So, for example, we can multiply everything by. You could do the same exact steps with matrices because there's a one-to-one relation between matrices and writing things out as a system. But I just wrote it this way because I think it feels a little bit more concrete. Okay, very good. Yeah, if you're doing it with numbers, you would just plug these numbers in and you can leave it as a fraction. And sometimes the fraction would simplify and it'll be like when we did a system of equation, we always saw that we would get nice numbers for x and y. Also, Jack, we're going to go back to the matrix in a second, and you'll see I'll show you how to kind of do the pattern, memorize this formula quickly using a pattern in the matrix. Okay, so what do you guys notice about these two answers? What do they have in common? There's one expression that they have in common. So so these are the answers. These are the answers that just depend on the numbers that you have in your system. You can, if you have these numbers, you can just plug them in and get x and y. But what expression do the answers have in common? It's always going to be some sort of subtraction, that's right. But look at these answers. Do you see anything that they share? Mm-hmm. They definitely have a BC. Anything else? They also have AD. So therefore, what do these guys have in common? Do you guys see the denominator is the same for both of them, which is pretty neat, right? So this expression, AD minus BC, it tells us that something very useful. A solution to this problem will exist as long as AD minus BC. Remember, what do we never want to happen in the denominator? What's the only kind of problematic thing that could ever happen in the denominator?
You don't want it to equal 0.
Yeah, we don't want it to be 0. Perfect. So we don't want it to be 0. So as long as it's not 0, we can use this formula. We can solve for x and y. Okay, now let's investigate what this pattern actually is doing. And this pattern is called the determinant of the matrix. And if you notice, it doesn't have anything to do with the augmented part. So if you write a system like this, A, B, C, D, E, F, we define the determinant of a matrix, A, B, CD as this this cross multiplying thing, kind of, where you multiply this diagonal AD and you subtract this diagonal. Maybe I'll do it in colors. So you multiply this diagonal, and you whatever numbers that is, you're gonna add those, and then you put a minus sign in front of whatever BC is. So this is a minus, and then this one is a plus. And so the formula is AD minus BC. This is the determinant of a 2 by 2 matrix. Maybe I'll write it out here, determinant. And the reason we call it a determinant is because if it's 0, then it determines that there's no solution. But if it's not 0, then we know that our system, regardless of what E and F are, our system will have a solution. You could write, yeah, we always start with the main diagonal first, and then you subtract the other one. That's kind of the standard way of writing it. So the formula is AD minus BC. And so here's the, if you notice, the numerator of X, do you guys see that it has a similar pattern to the denominator? Oh, let me just back up 1 second. Do you guys remember those problems? The one from the test where I ask, what would make, what kind of situation would make, so this is just a little bit of motivation, but do you guys remember that question? I said, what situation would of A, B, C, D would make this system have no solutions or infinitely many solutions? What's the key idea for these coefficients? What equation did you have to set up if you wanted to solve that question? We wanted to make them be in the same proportion, or in other words, we wanted to make sure that they're parallel. So to make them parallel, I told you guys, you want to look at their ratios. So if you look at this, I'm just going to write this as a side note over here. Just recall, the lines are parallel means the ratio A to C equals the ratio B to D. And if you cross multiply and subtract and rewrite this equation, what you observe is that's the same equation as AD equals BC, which is the same equation as AD minus BC equals 0. So that's kind of why the determinant is related to whether or not there exists an actual solution, or maybe it's going to be infinitely many solutions. So as long as it's not 0, then the lines are not parallel and you're going to have a nice solution. But if it's 0, you can get some weird things happening. So that's kind of a little bit of motivation. We'll see on Monday, maybe at the end of this class, we'll see another explanation of what the determinant means. But that's one kind of idea you can have, and it connects to why is there a negative on the outside for finding y? Oh, okay, Archer, that was a good question. I put the negative there just to make the denominators look the same. So you don't need to have a negative there. I just wanted to make the point that if you can rewrite it so that the denominators look the same. Okay, now here is Cramer's rule. Do you guys see that the numerator, or I'll ask you if anybody can make an observation. Just stare at this, a solution for x. How does the numerator differ a little bit from the denominator? And this is just looking for a pattern. There's no meaning or anything. No, you don't have to have any understanding. It has an f. Nice. There's an E. Nice. Yeah. Yes. There's an E and F, And the E and F nicely have taken place instead of the A and C. So let's look at that in terms of the augmented matrix. So if you look at what X, the numerator is, what it has done is you take your target, which is the augmented part, and the target shows up in the numerator. You take your target, and if you recall, this is the X column, this is the Y column. So you take your target, and instead of AC, you plug in, or let me write it like this, you just plug in EF. So to get X, I'm going to write it like this. This is Cramer's rule here. X, the formula for X is the determinant of EF BD divided by the determinant of AB CD. So all you do is to get X, you replace the X column in the original matrix with the target column EF, and that will get you to X. Let's try it out for Y. Let's see if it works out. So for Y, the numerator was, if the denominator is AD minus BC, which is the regular determinant, the numerator is AF minus EC. So F replaced B, right? Because this would be, oh, sorry, F replaced D and E replaced B. So let's take a look at that and just double check. Wait a second. Did I do something wrong here? F replaces D. Oh, no, that's right. F replaces D and E replaces B. So just kind of looking at it over here, you can see, yeah, F would take place of D. So F gets moved to here, and E gets moved over here, and you can take the determinant of that result. Okay. So the formula is for Y, you do the same pattern. So the denominator is the same. It's the determinant of A, B, C, D in the denominator. But the numerator now, the target numbers on the from the augmented part, they replace the Y column. So this is going to be the Y column. So you have AC, but here you're going to have EF. And if you look at the formula, this is AF. The determinant here is going to be AF minus, oops, yeah, AF minus EC. And that is what we found. Okay. So what it tells us is that the solutions, X and Y, are these neat ratios of different determinants. And it's a determinant it's always going to be a determinant of a 2x2 matrix, but the numerator, you have to swap out a column with a target. Let's try it out an example so you actually see, let's do an easy example so that you can see how this actually gives you the answers. So let's do the following. X plus Y equals 5, and 2x minus 3y equals negative 5. I believe that, oh, no, 2. Yes, okay, I like this. So please solve this using, practicing using this method. And the homework has a bunch of these as well. And after this, we're going to go to, I'm going to show you, it's the same pattern for 3x3 using this determinant. We're not going to do the first part where we did like elimination, because that'll be a little bit intense to do it. But I'm just going to give you the answer, and I'll define how to find a 3x3 determinant. But for now, just please do this and let me know when you got the answer. And also, if you need a little bit of help, just message me. And hopefully, as you're kind of seeing this, you see that there's a lot of there's quite a bit of depth that's happening behind the scenes here. Like, why is there, why do the answers come out as a ratio of determinants? Yeah. Okay. So so we first set it up. We want to put it as a matrix system. So we could write. I'm going to write it. If you recall, I'm going to write it the way I did last time. So not as an augmented part, but as a matrix 1, 1, 2, -3 times the vector xy. So this is yet another way you could write it, equals 5, -5. Okay. So I want this matrix times the vector xy gives me 5, -5. I want to figure out what xy are. So Cramer's rule tells me something really convenient. It says to find x, I can do this determinant formula. The determinant pattern of a matrix, of a 2 by 2 matrix, is always the same thing. It's the green diagonal minus the red diagonal. Nice, Jack. Nice. You got it. So you would take here the determinant. Let's do the denominator first. So in the denominator, you write the determinant of 1, 1, 2, -3. And you can just calculate that. And then the top, recall, this is your x column, this is your y column. So to get the x answer, you take the target and you just replace it. Instead of the x column, you replace the target there. And you take the determinant of that. So you get a determinant of 5, -5, 1, -3. And now you just have to be careful and do your determinants. Okay, so the determinant on the bottom is going to be -3, because 1 times -3 is -3, minus 2 times 1, which is going to be just -5. So the determinant on the bottom is -5. Is that any questions so far on any of these steps? Please just jump in if I did a miscalculation or. And then in the top, the determinant is -15. And you have to be careful with determinants. You got to be really careful with the minus signs and remembering that sometimes if you have two negatives, it adds. Minus -5 times 1. So that becomes -10. And -5 over -10 over -5 is just going to be +2. And then you do the same idea for y. The nice thing with these is you don't, because the determinant repeats in the denominator, you don't need to do this calculation again. So y would be equal to the determinant of 1, 2, 5, -5. And the denominator would now just be -5, just from the last part. And then doing this here, you get, you have to multiply your diagonals and subtract them. So what do we get? We get -5 minus 10. And this is over -5. So this is going to be -15 over -5, which is 3. And that's it. And you can check your answer and see that it works out. Any questions on this approach? Did you guys also, I saw a few students get it. Please hit yes if you got these and you feel comfortable with at least the mechanics of how it works. That's right, Archer. It is a bit, I would say, like, very surprising that there's such a nice. Lily, good question. why do we do this? This seems like you're doing like you're calculating these determinants. What's the reason for doing it this way? Because like elimination, I think, is a little bit easier for a 2x2. So for 2x2, Cramer's rule is not very useful. It's neat, but that it works. But I would say if you remember for 3x3, like doing all the elimination steps is really tedious for 3x3 and very prone to error. So I'll show you how to do determinant of a 3x3, and then you can apply Cramer's rule through a 3x3 and solve that without having to do elimination by hand. Archer, and also these methods, like Cramer's rule does have some, understanding Cramer's rule does have some applications, like more theoretical applications as well. And practical, the other, another good answer to your question is like, this is something like if you ever needed to write an algorithm that would solve a system, you can just plug in this formula. This is an exact formula that gives you the answer. So that's another advantage of Cramer's rule. Okay. Any other questions? You guys are asking really good questions, and I hope. Emily, did you have any questions any part where you were a little bit confused that I could address? Okay, what does determinant mean exactly? So for now, I would say the determinant of a matrix is this formula. So for a 2x2 matrix, it's this. And I'll show you what the formula is. I'll show you what the formula is for 3x3, and then maybe on Monday I will share what this quantity actually represents, because it has a nice geometric meaning. But for now, it's just a formula that you can calculate from a matrix. And the reason it's called determinant is because it tells you a lot of information about the matrix. If the determinant is 0, the determinant is 0, it tells you that the system won't have a good solution. But when the determinant is not 0, because your denominators won't be 0, then you can find an answer. Okay. Yes, Emily, which part did you get? Do you feel so? Yeah, don't worry too much about the vectors. We'll do that again a little bit on Monday. I think in a slightly easier way to grasp. I think the discussion on Tuesday was definitely. If you felt lost on that one, don't stress, because that was just a little bit of motivation and some food for thought. But which part were you okay with this last kind of example problem? And there's no kind of I'm not actually giving you any sort of deep explanation of why this is. Okay, Emily, yes. So this is not usually the way I like to teach. Don't worry, you don't have to understand what a determinant represents or like the meaning behind it. It's just a random formula for now. Just think of it that way. It's a formula that happens to show up, and it happens to show up when we do elimination. It's the formula that shows up in a pattern in the denominator. And if you look at the box of numbers, to get this formula, you just say, okay, I do AD, I do the top left to the bottom right, and I do bottom left to the top right. That's it. It's just a really random formula. And we'll see maybe why this formula is important. We kind of got a sense of it earlier why this formula AD minus BC is useful, because it's related to the lines being parallel, like this. That's some of the inspiration for it. But for now, I'm about to show you another formula, which is just got to know the pattern. Don't have to know like why the pattern is true, or it's just a definition. And then the cool thing is, once you know this pattern, you can take the determinant of any 2 by 2 matrix, and this pattern helps you to remember the, it's an easy way to remember these formulas. Because otherwise, these formulas look, they have 6 different numbers arranged in different ways. It could be difficult to remember. So the only thing that we're using this determinant for now is to help us get these numbers, or get these expressions, without having to memorize too much, just memorizing kind of like that the target column goes into the column that we want, and if you know how to do determinant, that's all you need to memorize. So that's all we did. And I totally agree that learning things this way could make you feel a little bit uneasy because you're just like doing some random formula and it's working out. But it's just a pattern for now. Okay, so with that said, let's do a 3 by 3 determinant. This is just going to be learning the pattern. There's no interpretation or anything behind it. And unfortunately, determinant, to be honest, determinant is one of the deepest ideas, I think, in math. It's something, I learned it also when I was about your age in high school. And later I got to see other interpretations of it. It shows up in lots of places in math. And so, I understand why it works, what it represents, and all that stuff. But it still is like, it's still very mind-boggling why it works and why it represents what it does, which we'll see next time. So it's one of these things that's like a little bit hard to wrap your head around. That's such a like intricate little intricate pattern, but yeah, it's a really neat idea. But yeah, let me show you now. And by the way, determinant only works for 3 by 3 matrix. Sorry, for a square matrix. So that's the only time you can have a determinant. So let's do determinant of a 3 by 3. So here's how we do it. A, B, C, D, E, F. And I'm just showing you a pattern now. It's kind of like, I don't know. You can think of it as like an arithmetic shortcut or something. Just the pattern. There's no meaning or anything. I'm not explaining the meaning behind it. Okay, so we can find a 3 by 3 determinant. I'm going to show you 2 ways to do the 3 by 3 determinant. The first way is really important because it will, once you understand this pattern, it will allow you to find the determinant of a 4 by 4, of a 5 by 5, and higher. So what do we do? And there's a lot of amazing things that show up here. So the first is you make a grid on the top row, plus, minus, plus. In fact, you can actually extend this checkerboard grid any way that you want. You can extend it to the first column. You can do the middle row, but you start with a plus for the top left, and you make a checkerboard plus minus pattern starting from the top left. But I like to always do it from the top row. So I'm going to erase the other ones. But just keep in mind that this way I'm showing you, you don't have to use the top row, but you do have to put a plus in the top left. Okay, so how do we find the determinant of this guy? So this formula is the following. Have you guys played, just a show of hands, if you played like a little bit of Candy Crush? Have any of you guys played like some Candy Crush or Bejeweled? Some of those games? Oh, okay, nice. A lot of hands go up. Okay, great. I think Bejeweled, Did they have this thing where like when you get like a certain combination, you cancel out like rows and columns? Nice. Like they get cleared out. So have that in your mind because that's what we're going to do to this box of numbers. So the first thing that we start with is A. So we do A. We're going to go along this first row and we're going to calculate a bunch of things at each step. So we do A and we do a Candy Crush thing where we cancel out everybody and we're left with a box. This is called a, I believe it's called a minor, but the idea is you're left with a smaller matrix. So the term of the 3 by 3 determinant is to build it up is from a smaller one. You can do A times the determinant of E, F, H, I. Next, we do minus B. We do the Candy Crush method times the determinant of what's left over. So if you look left over, you see D, F, G, I. So minus B times the determinant of D, F, G, I. By the way, if you don't want to keep writing determinant, what people sometimes do with the determinant is they write it like this. They put it like they put a bar, so not a bracket. They put it just a straight line. It looks kind of like absolute value, but it's not. It stands for the determinant. So they write it like this. And so this is what they do in the book. So you don't have to keep writing determinant. Minus B times D, G, F, I. And then the last one will be plus C. And do you guys see when you do Candy Crush, do you see what's left over? It's going to be this matrix. So it's going to be D, E, G, H. Okay. So this is one way of calculating a 3 by 3 determinant. It's kind of like, you're taking the determinant of a smaller 2 by 2 matrices. The trickiest part to remember when you're learning this is all the minus, like being careful with this minus sign. So don't forget that you have to do this minus sign. How do you guys hit yes if you feel comfortable with kind of the pattern? And we'll do an example in a second. Cool. Let's try an example together. So I'm going to put the formula up here. And let's just do the determinant of a 3 by 3. Let's find the determinant of 1, 2, 3, 4, 0, minus 1, 0, 2, 1. All right, guys, please calculate the determinant of this one. And also, if you need some help, that's all right. We got one answer. I should probably do it myself. Let's just double check. So I'm going to do, I like to write plus minus plus. That helps me. Just like different colors here, plus minus plus. And I'm going to start doing it. I'm going to do 1 determinant. And it takes a little practice doing determinants, being careful with the minus signs. 2, 1. minus 2 times determinant of 4, 0, minus 1, 1. Oops, I don't want to bracket there. That's because I'm not writing determinant. I'm using the bars. Plus 3, and then what's left over is 4, 0, 0, 2. Okay, so now I'm just gonna, nice, all right, excellent. I'm getting a few students that are getting it right. Well done, Kanjit, well done, Gabby. So calculate here, it's gonna be 1 times 1 times 0 is 0, so that's gonna be 0 minus negative 2, minus 2, and then in here I have 4 times 1, which is just 4, minus 0, because that's nice, that's just 4, plus 3, and that's going to be just times 8. So this becomes 2 minus 8 plus 24, which is 18. Alrighty, nice guys. So that's one way you can do the determinant. It's really nice if you know 2 by 2. Be careful with minus signs, but it's a nice approach to do it. Let me show you another way you can do determinant that I like for 3 by 3s because it kind of reminds me of the pattern for 2 by 2. But by the way, let's just continue with this a little bit more. You can extend, the cool thing about determinant is it extends to 4 by 4. So if you wanted to find the determinant of a 4 by 4, you do the same exact thing, but you're going to need to do Candy Crush method with the top row, plus minus now. And then the Candy Crush, when you do Candy Crush method, you're going to have to do 4 3 by 3 matrices. And then you do the 3 by 3 matrices doing it this way. And so it kind of like, it's going to be like a lot of work, but you're just cascading it down. So you can always break it down into 2 by 2 matrices. Oh, 18, what it represents? Well, I'll leave that for next time, I think. I'm not sure we're going to have a chance to explain what that is today. But it represents something you understand. It's something really, really nice. And that's what's so amazing about the determinant. Okay, let me show you one more way to do the determinant. And for the homework, you don't need to understand kind of where it's coming from. Like you do need to know how to do the formula to apply Cramer's rule. That's all. Let's do another way. So and on the test, by the way, you can use either way of calculating the determinant. One of the other ways that I'm about to show you. But this way that I showed you is really important because it's the way that generalizes to find 4 by 4 determinant, 5 by 5, and you can keep going on and on if you wanted to. The other comment I'll make is the Candy Crush method. I chose plus minus plus on the first row, but if I extend that grid, there's a really amazing thing that you can do. Plus minus plus, plus minus minus plus. You can actually, you don't have to pick the first row. You're actually allowed to pick any row or column that you want and then do the Candy Crush method, and you'll still get the same answer. So that's a really surprising fact. But generally, I pick the first row. Sometimes if you see there's a row or column with a lot of zeros, you might want to pick that one because that will simplify. Like if there's a 0, you don't have to do a determinant when you do the Candy Crush method, right? Because that 0 will kill it off. So technically, maybe I would have chosen, if I wanted to take advantage of that, I would have chosen to use this row. So I do 4 and do Candy Crush here. 4 times the determinant of 2, 3, 2, 1, then 0 times do Candy Crush on 0. Well, I don't have to define the determinant because it's going to be multiplied by 0. And then do minus 1 times the determinant of 1, 2, 0, 2. But I have to remember these signs, minus, plus, minus. You have to take into account the grid. So it's a really kind of incredible formula that it works in all these different ways. but let me just show you one other way that I like. And then once you see this way, it's up to you. Try both of them and see which one you like more. So the second way that I like to do it, and this is only good for 3 by 3, is I write it like this: 2, 3, minus 1, 1, and I just copy over the 2 rows. So I get 1, 4, 0. So this is my matrix. And all right, 1, 4, 0, 2, 0, 2. And I kind of like in a 2 by 2 matrix, when you do the determinant, you take one diagonal, you take the other diagonal, and you subtract them. So this formula kind of extends that pattern, but if you were to do the diagonals for a 3 by 3, just the diagonals, right? Just these two, you would miss a bunch of numbers. These numbers wouldn't be included. So this pattern sort of takes that into account. So what this pattern does is multiply the diagonals that go from the top left after you've written them next to each other like that. So multiply all these numbers, and let's see what we get. So 1, 0, 1, that's going to multiply to 0. This multiplies to 0. And 3, 4, 2 multiplies to 24. Okay, now we're going to multiply the other way. And I'm going to draw it in here, but if generally if you draw this, like, it might start looking a little bit messy, but something like that. Multiply that one and multiply that diagonal. So, and you're going to subtract those. So this is going to be 0. This is minus 2, and this is 8. So grouping all those together, you get minus 6. Oh, sorry, you get positive 6. And now putting the pieces together, taking the bottom number and subtracting the top number. Oops, that's cool. So you get 24 minus, let's say minus the 6, and that gives you 18. Okay. So these are two different approaches to doing 3 by 3s. So let's just take a quick survey. Please hit yes if you like the first approach better, and hit no if you think maybe you'd like the second approach better. And it's really personal. Like, I have students like either one, so I'm just curious how you guys, what the vote would be. Maybe we have to do a recount later. Oh, it's pretty spread out. It's pretty break even. Nice, guys. Cool. Yeah, I'm a fan of the second one, but the first one is nice because I like the pattern. Okay, now just the last thing here is, well, how does this connect to Cramer's rule? The awesome thing is, once you know what a determinant is, Cramer's rule is exactly the same for a 3 by 3 system. You just have bigger matrices, but the idea is exactly the same. So let's see here. Let me just look up whiteboard notes. Let me look up one that we did, Gaussian elimination here. Okay, I'm not seeing that. That's not a good one. Oh yeah, okay. Let's do the one that we did in the homework review, 8.613. So that was this matrix. 3, 2, 2, 1, 2, negative 1, 2, minus 4, 1, 3, 5, 0. And we saw the answers already. The answers were 2, 1/2, negative 2 for x, y, and z. So So let's solve this using Cramer's rule. Oop, that's not what I want. I want this guy. Okay, so this is our augmented system. It might have been given to us with x, y's, and z's, and we made it as a matrix. So here's what we get. The solution for x is going to be the following determinant. You take the target, the augmented part, and you replace the x column with it. And you take the determinant of that resulting matrix. So it's going to be the determinant of 3, 5, 0, 2, 2, minus 4, 2, minus 1, 1. And here I'm writing the determinant. You can use the bars if you prefer. And the denominator is going to be the determinant of 3, 2, 2, 1, 2, minus 1, 2, minus 4, 1. So all that work that we do, it just comes out to a ratio of these two different determinants. And to find the y, you would just replace the y column with the 2, 2, minus 4 with 3, 5, 0. Keep the other columns of the matrix the same. All right, let's try this out. Take some time to do this one, and we'll see what answer we get for x. The nice thing is with Cramer's rule is once you get the determinant of the denominator, you can keep reusing that same number over and over. So to use Cramer's rule to solve a 3 by 3, you have to calculate a 3 by 3 determinant 4 different times, which is annoying, but maybe not that bad. I don't know. It is all of the solutions of solving 3 by 3 systems are annoying. There's no way of getting around that, but it's at least it's very, very systematic. Okay. I'm going to do the second way of calculating the determinant, but you're welcome to do any way. If you want to follow along how I'm doing on the board, I'm just going to do it quietly, and you guys can try it out on your own, and then we can compare answers in a little bit. So this is going to be. I'm going to just write it over. And it never hurts to give yourself extra space with these so that you're not making any mistakes. Negative. Okay. No. Thanks, Emily, for letting me know. That's no problem. All right. I got the numerator here. If you want to check your work, I might have made a mistake as well. With all these approaches, there's a lot of numbers and minus signs floating around. So, Let me know. 46. Let me see. Is maybe 46 is better? What did I do? I got 12. I don't know. I got 6. Negative 20, negative 40. So that's going to be negative 34. And then that's going to be 12. That's 0. Anaya, do you see any step where we went? Did you do it the first approach or the second approach? Okay, so you did it the same way that I did? Yeah, any of those numbers look different? So we're all getting different numbers. Yeah, that's the fun thing about these. Anaya, yeah, do any of those numbers look familiar? 0, 12, 10, 6, 0, negative 40? Um, oh, wait, wait. Oh, hang on. So do you see, be careful with the minus sign. You want to make sure that that 40 would be negative 40. And then I think somebody else got negative 12, but negative 4, negative 1 times 3 will be positive 12. So be careful with the minus signs in the actual matrix, because the numbers on the top and bottom might have minus signs or might not. Okay, so let me do the denominator. The denominator would be 3, 2, 2, 1, 2, minus 1, 2, minus 4, 1. And then I'm going to do 3, 1, 2, 2, 2, minus 4. Or just kind of, yeah, whatever. I don't actually need this thing. Okay, let's do these guys. This will be, this is 6 minus 4 minus 8. And the red one is going to be 8, 12, and 2. So this is going to be 6 minus 4 minus 8. That's going to be negative 6 on the bottom. Minus 22. Uh-oh. Oh, no, that's not bad. That's good, actually. This is minus 28. Okay. Yeah, okay. Yeah, that's right. There was a negative 4. There was this negative 4 here. This one came from here, the negative 4. So that, I think that's what made it negative 40. Okay, and now you can just put it into the formula. This would be negative 56 divided by negative 28, which is going to be positive 2. And that was one of the answers from the last time. And then you do the same thing for y and the same thing for z, just replace a different column. And it's a good practice. The answers, if you want to keep practicing here, I just have the answers right. You can do the practice, you can check, you can continue for more practice. And the homework is also more practice. You can try y is equal to 1/2 and double check that you get z is equal to negative 2. So it's just 2 more determinants to do because you already got negative 28. So it's not too much work left to do that. And that's Cramer's rule. Our next midterm, which will be, I think we'll do it like right before Thanksgiving. Our next midterm will just have one of these questions where you have to use, I think maybe I'll do it for a 2x2. But I will ask you to know the formula for a 3x3. Archer, are you confused with why this is working, or just kind of the mechanics of it? Oh, okay. So you did the other method and you got different numbers. You did the Candy Crush method? Oh, okay. So which did you get? So you're okay with these? You're okay with these matrices? You got 24 for which one? For the denominator or the numerator? Okay, yeah. Be careful. It's very easy to like forget a minus sign somewhere, or when you're calculating the determinant to not subtract that diagonal. So and use the left side, not the right side. Oh, use the left side without the right side. What do you mean by that? I'm not trying to understand what that means. Mm-hmm. Oh, did you not put the minus on the 2 in the middle 2, the plus minus plus? That's an important, if you're doing that method, that's a really important thing. Oh, you did put it on. Oh, okay. Oh. Oh. Yeah, so just kind of, we could write it out here just to be careful, just to show the other method as well. So that would be 3 times 2 minus 4 minus 1, 1, minus 2, because there's a minus sign there because it's in the middle, 5 minus 1, 0, 1. And then the last one will be plus 2, 5, 2, 0, minus 4. And then doing these all out, this would be 2 minus 4 times minus 1 is 4. So it's actually, it's going to be subtracted though. So basically 3 minus 2 minus 2. Whenever you see a 0 in a matrix and a 2x2, it's nice because it's just going to cancel that column, that diagonal. The minus 2 times 5. And then this will be 2, another 0 showing up. So that's just 2 times negative 20. Putting these all together, you get negative 56. Awesome. And then you got to be careful with the denominator as well. The minus. Oh, gotcha. Yeah. Alrighty, guys. Please complete this homework over the weekend. Just practice the mechanics of it. I got it. Oh, yeah. Minus 56 is the answer to the numerator. Hang on. So the answer for x is you take the determinant of the numerator and you divide by the determinant in the denominator. So you got to find 2 determinants. And it comes out to, the one nice thing about these, especially when I give it on a test, is you'll get your 2 determinants, and they might be weird numbers, but they have to divide nicely into each other because the answer will be an integer. How did you do the bottom determinant? Same approach. I got negative 28. You can try it out here. It would be the same thing. It would be 3 times this determinant, and then negative 2 times 1, this guy, and then 2 times that one. So either way, you get negative 28. Try it out. See if you can catch. If you didn't get negative 28, you can also email me. I can email me a screenshot or a picture of what you did, and I can see if I can spot your mistake. Alrighty, guys. I hope you have a great weekend. Are there any other? Yeah, I'll post these notes right now as well. Take care, guys. Have a great weekend. You too. See you.